All right, and welcome to this video where we're going to look at a little more advanced iterative analysis. And by that I mean we're going to continue looking at using summations to do analysis of looping structures. But now we're going to look at summations that maybe are a little bit trickier, maybe a little bit harder to just analyze directly. And we're going to look at a couple techniques that we can use to find bounds on these summations as opposed to just finding exact closed form expressions. In order to do this, I'm going to again use a couple algorithms that hopefully we're already familiar with as a means to, as our subject matter for our analysis. And the first one we're going to look at, or rather the one that we are going to look at a couple different versions of, is the selection sort algorithm. And again, hopefully we've had a chance to review this before. If not, let's take a quick review through this version of it that I've added in this pseudocode. All right, so taking in a list to be sorted, A, the goal of this pseudocode is we're going to start with another empty list C, and we're going to add elements to that list, and we're going to add them in order so that the resultant list is sorted. And the way that we're going to do that in this loop here, so we're going to repeat until A is empty, we're going to first find and remove the minimum element from our list A. So this is going to be how we ensure that we add the elements in order to C. We're going to find and remove the minimum element, so we're going to find it. That would be the first one we'll add to C, and we're going to remove it from A to ensure that we don't select it on the next round. There's a couple of characteristics here that maybe we can verify quickly. We're not going to do a proof of correctness for this, but we can probably verify its correctness quite easily ourselves. One important characteristic that's probably going to be important to our analysis is that we do indeed remove one element from A on each iteration. And since we're repeating until A is empty, if A has n elements in it, then we should expect that there would be n iterations of this loop. And that's something that again will show up in our analysis, and indeed that's our first question. So we've answered our first question. There will be n iterations. So the next question then is, well, what is the cost of each iteration? And here it's going to be worthwhile to note that for pseudocode is definitely a beneficial tool that we can use. One of the reasons is that it can be very expressive. On a single line of pseudocode, we might be able to capture an entire loop, an entire subroutine call, and that means we could probably do on one line of pseudocode any amount of work as long as we have a nice, easy way to express that, say in a single sentence. So here we have a single sentence. Let C be the minimum element in A and remove it from the list. So there's a whole bunch going on there in that one sentence. We're finding the minimum element of A and we're removing it from the list. And we might think of those as two operations being carried out separately, but more likely it's better to think that we're doing that all at once. We're going to find it and remove it all at once. So we're thinking to ourselves, what is the cost of that? So again, here we're saying, what is the cost of each iteration? Beyond the cost of finding and removing the minimum element, we still have a couple other things going on here. We check to see if A is empty. We add C. We add the element to the end of our other list C. So what is the cost? Well, I've sort of listed this out here. We've got effectively four different things we need to look at. And again, it's probably worthwhile to lump 2 and 3 there together. Finding and removing the minimum element is likely something we're going to be doing all at once. Now let's think of these, each of these in turn. And in particular, I want to look at the first and the last one. The first and the last one, these are pretty simple operations that hopefully our experience looking at data structures and other coding examples leads us to say that these are constant time. So checking to see if a list is empty, that should be a constant time operation. Adding an element to the list, well, here it's the simple add where we just add to the end. And so again, whether that's an array implementation or a linked list implementation, we should expect the cost of that to be constant time. So that leaves really that one remaining operation, the bundle of those last two, finding and removing the minimum element. So again, your experience might make you think, well, we need to answer maybe a different question here, or a second question here. That is, well, what data structure is it that we're going to be using to store our elements? It's not immediately clear. We sort of mentioned a list above here, but it didn't really, what kind of list is sort of been left open. And maybe here we might want to fork our analysis and say, well, look, depending on what kind of data structure we use here, we might get different runtimes for this algorithm. So we want to be sensitive to that. It may tell us that some data structures should just be avoided. Maybe it means other data structures might be worthwhile. So let's keep our analysis open to those possibilities. All right, so now that we think about it, which data structures would be beneficial here? So first of all, the default one will be a list, where we've already assumed that as a default, we're sorting a list. But if it's not stored in a list, what other data structure might be useful when the operation that we are using here is to find and remove the minimum element. So again, hopefully with your experience, well, what data structure keeps the minimum element for us in a prime location? Well, usually a min heap keeps the min element on top, and of course the min heap is a good implementation of a priority queue. So maybe we have two options here for our selection sort algorithm. We can use a list, or we could use a heap, and that actually leads to two different algorithms. Selection sort is the name we use when we use the list, but if we use a heap, we usually call it heap sort, which is just another version of this same algorithm. In fact, it's exactly the same algorithm, just using a heap as the data structure. We're going to conduct our analysis of both of these versions. The first one is actually pretty straightforward, and you may have seen such an analysis before. Again, this will just be a practice of some of our skills. The second analysis, we will present some new skills that will allow us to come up with a type bound for the summation that we eventually arrive at. All right, so let's again here for the moment assume that we are working with a list. In this case, we decided that the cost of finding and removing the minimum element, as we stated here, for a list of size k, that would be big theta of k. Another thing that's maybe important for us to recognize here is that the list that we are talking about is the list A. The list A begins full with n elements, but again, we already argued that we're going to iterate in every iteration we will remove one element, so this will be about n iterations, and that's what informs the lower and upper bounds of our summation here. We're going to set them to 1 to n, even though no such bounds existed here. We're going to set them with the understanding that we're going to do n iterations of this loop. All right, so that's where that came from. Now, we also have sort of the two different sets of operations. We said two of our operations, checking to see if our list is empty, adding C to the end of the list. These were constant time operations. So for the moment, I've written in here theta 1. This isn't exactly right, but this is good, at least for our notes, to remind us what we're talking about here. This is the cost of those two constant time operations. Now this cost here, this is the one that I think is important. This is the cost related to finding and removing the minimum element of the list. And we might wonder to ourselves, why does this not just say theta of n? And the reason for this is we need to remind ourselves that while the list begins full at size n, as we remove elements from it every iteration, it gets smaller and smaller. That means the cost of finding the minimum element and removing it actually also gets smaller and smaller as we go. So in order to capture that, we need to have a function here that also gets smaller and smaller over each iteration. Now I is the variable we're iterating over, and because it appears in my formula here negative, that means as I gets bigger, as our iterations continue, this value gets smaller, the total value gets smaller. And we start here at n plus 1, but notice in the first iteration I is equal to 1, so the 1's cancel out, and we actually, in our first iteration, we end up having here theta of n. The next one will be I equals 2. We get n minus 2 plus 1, so we get n minus 1. So the next iteration will be n minus 1. We can see it's counting down. The last iteration, if we want to know what the last iteration is, we just need to jump up to n, plug n in for I, and we see n minus n cancel. We just get 1. The last iteration is 1. And that makes sense. When we only have one element left, the cost to find and remove it is constant time. We can just find it and remove it. Okay, so that's where these numbers come from. The 1 here is constant time, but that's why we have the n minus I plus 1, is to account for the fact that a gets smaller and smaller in each iteration. But as I mentioned, this theta notation is not actually correct, and I've written it here just as sort of my notes. In fact, you'll find other computer scientists write this as though it's correct, and you should say, no, that's not correct. These are sets. These are not functions. And so there's no way for us to add them together in this way. There's nothing that defines us. So this is bad notation. We shouldn't write things this way. So instead, to correct it, what I've done is I've gone into these sets and I've reached in and I've pulled out what I'm calling representative functions. Okay? And so, for instance, in the constant set, all I've done is I've pulled out some constant c, which I assume is a reasonable bound on the function that I have, the actual function that exists in here. Now, what do I mean by that? Well, since there is some constant that must bound above and below the function that is represented here, that is the definition of theta, that there's some constant above and below that bounds this constant here. Well, c might be one of those constants. That's all I've done here. If I'm looking for an upper bound, we'll assume c is an upper bound. If I'm looking for a lower bound, we'll assume c is a lower bound. Likewise here, for this theta class, we want to pick a representative function. Our instinct might be just to pick what's written in here, n minus I plus 1. Again, the problem here is we're not guaranteed that the function that is actually represented here is less than 1 n minus I plus 1, 1 being the leading constant out front. Here I've written it as d. We know there is some constant by the definition of theta for both an upper and lower bound again. And here we're going to say, well, we don't know what it actually is, but we know one exists, so let's give it a name. Let's call it d. To correct our incorrect notation up here where we put sets in the sum, that's not something we're allowed to do. Instead, we will write it like this, where we've selected some constants out front. So here we've now got a sum that represents the cost of our selection sort loop. All right, so we've now got our sum here. Again, this expresses the runtime of our algorithm. And now what we want to do is simplify it. And to simplify it, again, we're going to use the same technique we used in the previous video. We're going to distribute our sum over our terms, and I'm actually only going to distribute it over these two terms now, so that I can show you a little technique or a little trick we can use to make this a little easier on ourselves in a second. But let's just distribute the first one, or let's just distribute the sum across the two terms for now. So our first sum and our second sum with the same indices, but our second sum, I'm going to leave these three terms all gathered together again, so that we can tackle it in a second. All right, we can actually simplify this one quite easily. Hopefully, some of the techniques are becoming a little bit easier for us. Remember, we're going to bring the c out front since it doesn't depend on our I. Right? C doesn't depend on I, so we can factor it out of the sum. That leaves us with just n ones. So if we want to write on the next line here, we're going to this next sum is just going to end up being a c times n. Up next, we've got this second sum here. And again, for this second sum, I do actually want to simplify it. And to simplify it, I want us to look a little bit closer. Well, one thing here is we can bring the d out front. So maybe I will just bring the d out front. So all we have to worry about now is this sum. I'm going to, for the moment, I want to rewrite it in a second, but how am I going to rewrite it? Well, let's take a look here. Let's go back and look at what we had. We designed this sum in a specific way. We wanted the very first value in the sum to be n. And let's just verify that again. N minus 1 plus 1 gives us n. Okay, so we've got n. And the next element in this sum is going to be n minus 1. Again, 2, we plug the 2 in, we get n minus 2 plus 1, that gives us n minus 1, and so on. So we get n minus 2 plus dot 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 plus 1 at the end. Remember, we plug in the n, we get n minus n, it gives us 1. Okay, so this sum, we want to, this sum here asks us to add up these numbers in this order. Now, the beautiful thing about addition is if we add them up in this order, of course, we get the exact same result. And we can write the sum differently in that reverse order if we notice that it's just 1 plus 2 plus 3 all the way up to n. We're just asking to add the i's together. So this sum here, even though it looks a little bit messy with the 3 terms, we can rewrite as this sum here. So again, going back here to finish off my solution, or my sum here, we've now got a simpler sum to work with than this one up here. Now, if we did choose to distribute our sum over all 3 terms, we'd actually end up in the exact same result. And so there's nothing wrong with doing that. The only thing is we would end up with a couple extra lines of math. So if you want to, save yourself a few pen strokes, then you might want to remember this trick. And of course, I'm sharing this trick now, just so you have an extra tool in your toolkit. As you're trying to, work with sums of your own, you might encounter something like this and say, aha, I remember this trick where I can reverse the sum. Okay, and when does this trick become useful? Well, I'll just point it out here. When this I value, the index we're summing over, is negative, so usually it's in an n minus I kind of scenario here. The plus 1 just helped get our indices line up right. But if you see like an n minus I showing up, that means you're probably counting down instead of counting up. Well, if you turn things around, then you'd count up, and things usually look a little bit simpler on that side. All right, then let's once again remember that this sum here, I was calling it Gauss's sum in the previous video. So since we've already looked at that sum, we can remember what it's equal to. Our d remains out front, but this sum itself we can rewrite as n plus 1 all over 2. Okay. And again, this sum, it doesn't take us too much effort to see. We're going to get an n squared in there, and maybe I'm going to just skip to the punchline then. This is an n squared algorithm. Of course, again, maybe not too surprising. We know that our selection sort is an n squared sorting algorithm. I've included some of these, some of the tricks we've got here as well. So we did reverse the sum. I call this trick reversing the sum. Some of this math here is similar to what we've just gone through. We simplify the first sum, then we reverse the second one. So here we reverse the second one. After we do that, we find what it is equal to. Here I've actually simplified it down even further, and we result in the same conclusion that we're in theta of n squared. And we've skipped over the formal proof that it's in theta of n squared. Of course, using the techniques we reviewed in a previous video, we should be able to do that. Let's once again pivot. Now we want to focus our attention on the other version of this algorithm, where instead of using just a straightforward list, we're going to assume that the elements are stored in a min heap. That way, finding and removing the minimum element no longer takes us theta of k, where k is the size of our list. Instead, it's going to take theta of log k. Okay, log k. Now, what that does is it changes our the function that we have in our sum. Our sum is still going to be the same. The code is still the same. We're removing one element at a time, but now we're removing it from the min heap, and that no longer takes us that theta of k, and now takes us theta of log k, which we express here, being careful to remember that just like the list would get smaller every time, our heap also gets smaller every time. So we start with log n, and it will go down to log of 1 in the last case. All right, so here we have that expression for our sum. Let's go ahead and see what we can do with this one. A little bit of simplification we can do to start out. It will be similar to what we've done before, so I'll go through that quickly. First thing, we can distribute our sum and simplify by eliminating the first sum. We'll also factor out the d, and then the same thing will be true that we saw beforehand, and here it becomes critical. We didn't have to actually reverse the sum in the previous one. It merely saved us some calculations. Instead, in this case, if we don't reverse the sum, we have to deal with that nasty n minus I plus 1 inside the logarithm, which could become problematic. But by reversing the sum here, we get a much simpler sum where we just have straightforwardly log I. How do we solve this sum? Do we know what the sum from 1 to n of log I is? And in fact, this is a question that there is a correct answer to. There is a known answer to this. The known answer, if you do know it, is not very helpful, so I'm not actually going to review it at this time. If you are pretty good with your logs, you can probably figure out what the solution is going to be. And I'll just hint at it maybe with the idea that I'll give you the hint by saying, well, what is the sum of 2 logs? Because here we've got the sum of n logs. So if you can figure out what the sum of 2 logs is, if you can rewrite that in a different way, you might be able to know what the sum of these n logs are. And again, it's for mathematician interest's sake, it might be worth knowing, but for computer science sake, well, it's not going to be as helpful, because really at the end of the day what we want is we want a tight bound. We want a upper and lower bound on this sum. Again, I've now focused in on just this sum. Again, it's a little difficult to find the exact formulation. So what I'm proposing is that we look for 2 functions here, u of n and L of n, I'm calling them. One will be an upper bound, one will be a lower bound. And we want, or at least our goal will be, that both u of n and L of n are in the same theta class. And so here I'm saying that they're both in theta of g of n for some function g of n. If we can do that, then that means that the sum here must also be in theta of g of n by what we call the squeeze theorem. And so again, if we can find these 2 bounds, the upper and lower bound, such that they both have the same theta bound, we call this a tight bound, then then it guarantees that the sum itself also has that same bound. And again, here we're just applying the definition of theta. The upper and lower bounds here are really just applying the definition of theta. And I'm going to present the technique here by looking at both the upper and lower bound one at a time, but also keeping in mind here that this technique, the upper bound is going to be the easier one. So we're going to do that one first. It's usually the one that's going to be more relevant and more important to us anyways, so usually we do it first for that reason. But again, it's the easier one, so let's take a look at it here. Now, we're doing an upper bound, so I want to do less than or equal to. But again, we're doing an approximation, so once again we have tools that we can use here. Tools that we maybe don't have in the equation environment where we're doing an equal to. Now in this case, what we're going to actually do is we're going to try and overestimate this term. Now I call this binding the term. What we're going to do is we're going to try and overestimate the term. And to do that, we're going to look closer at the log function. So first of all, the log function we know is an increasing function. Over time, it increases, which means that the largest that this term gets out of all of our terms, the first one's log 1, then log 2, and so on. Those keep getting larger and larger until we get to log n. So the whole sum must be less than or equal to, if we rewrite the sum here, log n. So here I've replaced the log I with log n, making it larger in every case except for the last. Now that I've done that, this term no longer depends on I, so we're actually able to simplify quite easily now. We just bring the log n out front. We're left with nothing inside there. This sum, of course, becomes an n, so we get n log n. And maybe quite importantly, notably, there's sort of this invisible 1 out front here. That's our, if we need to select it, that's our b right there. Sorry, that's our b right there. But again, that allows us to show, oops, I put a theta there. That's not correct because we've only done the upper bound. So we've actually done big O of n. That's our upper bound, quite easy. The only technique that we've used here is this one here. This is our new technique, and I'm calling this one binding the term, where we try and find an upper bound on the term. So again, we're going to work with this sum, but now I want to go the other direction. I want to find a lower bound. Now finding the lower bound is a little bit tricky here because we have, well, let's try. Let's just see what we can do. I'm going to try and use the same technique that we used above here. Above here we said, look, the largest our log function is when we plug in the largest value, which is n. So let's do that. Now in this case we want it to be small, not large. So the smallest that we get is when we plug in log 1. All right, now some of us might already see where this is going. Log 1, of course, is also very easy for us to figure out. This is I equals 1 to n of 0, because log 1 is just 0. Well, the sum of n zeros is 0. So we've gone ahead and said, well, look, I can go find a lower bound on this sum. All I've been able to prove here is, well, there you go. This sum is bigger than 0. Well, that's probably a little bit extra work we needed to do just to know it was bigger than 0. We probably already knew it was bigger than 0. So we haven't really gained anything in this step. So I guess, you know, good job, I guess, good effort for finding a lower bound. You didn't mess up your math, but not tight. Okay. Oh geez, look at this. I went and wrote n up here when I went and said this was n log n. Good thing I went up here and checked. That's what our bound should be, not log n. Oops. But the point that I was trying to make here is that this 0 does not match our bound up here, and we want a bound that does match. Otherwise, it's not a tight bound. We've got an upper bound of n log n. We want a lower bound of n log n, and we didn't do that here. So even though this tool works, this is a correct tool, it over-approximated it. It gave away too much. We don't want to give away that much. So we have to come up with another technique. And we are going to use this technique again, but we just have to do something first. In this sum, what we want to do now is I'm going to do a technique that's called splitting the sum, and I'm actually going to be pretty deliberate here, so it's going to take us a few steps. I'm going to make the first one go from 1 up to the floor of n over 2. Okay, but I'm still going to have log I here. Now that's the first half of my terms. Put the floor in there in case n is odd. Okay. Basically, I'm saying let's take the first half of the terms. All right. That's only half the sum, so I've left out the second half, so let's rewrite the second half over here. The second half is going to start at n over 2 plus 1, and we're going to go up to n, and it's also going to be of log I. We can now use this technique that we just used above here on both of these sums. Now the first sum we'll see is just going to give us a log 1 as a 0. We're just going to take this one and say 0 for it. So we're going to say, okay, this is greater than or equal to the first sum, that's a 0. Okay. And we're just going to leave ourselves with the second sum, and for the moment I'm going to just rewrite the second sum so we can see. The reason I'm going to do that is in a few we're going to skip over these steps, and we're just going to skip straight to this step where we've got log I here, where we start at the floor of n over 2 plus 1, the next term up, and we go up to n. Okay, so we've now eliminated that first sum. So if we do the whole thing in one step here, so if we went from here to here, what we're saying is the sum of all the terms is greater than or equal to the sum of half the terms. And that should make sense. As long as we have positive terms, the sum of all the terms must be greater than or equal to the sum of half of them. So we're finding a lower bound, and we're doing that first by throwing away half our terms. And luckily, we're actually throwing away the smaller terms, so we've left with the bigger one, so we haven't actually thrown away as much as we maybe thought. So now we need to deal with this sum. How are we going to deal with this one? Well, again, we're going to do the next step here. The same technique we did above here, but now we notice our lower bound is no longer a 1. When it's a 1, we get the 0, but this one's no longer a 1. So now we're going to get, well, this one's going to start looking a little bit messy here. Floor of n over 2 plus 1 n of log of the floor of n over 2 plus 1. And I guess I should put that all in my log here. So again, noticing now after that this term no longer depends on our I, so we can bring it out front. So I'm going to continue here. Now I'm going to remind ourselves of a sort of a notation that I use. When I do steps that are algebraic, I usually use an equals. When I do steps that are approximations, I use a greater than or equal to, like this last step where I approximated the I with the floor of n over 2 plus 1. That was an approximation step, so I did that. But in my next step, I'm just factoring this out front, and that's just an algebraic step. And since it's an algebraic step, I'm going to use an equals sign. Okay, so this one is equal to log of the floor of n over 2 plus 1. So that's this term here moving out front. And then we're going to write our sum. Now this sum is still the same, but we've now factored out this term, so we've got the 1 here. All right, and that raises a question now, what would this sum be equal to? Now, this brings up maybe a couple interesting sums that maybe I'll just bring down here for us to write. A couple of some identities that maybe are worth knowing. Say we have a to b of 1. Okay. Well, this is going to be equal, let's make that a b. This is going to be equal to b minus a, which makes sense, but plus 1, and we need to remember the plus 1 to count a as well. We start at a and then we go up to b. If we just do b minus a, it's as though we started at a plus 1. Okay, so that's important because that's the kind of sum we have here. So that means if we plug in our sum here, maybe let's continue with this formula. So we've still got our log of the floor of n over 2 plus 1. That term's still there. But now we're going to replace this term here. Well, actually, maybe I'm going to do this on the side too, so I don't have to keep doing my writing it down. Let's take a look at what this is going to be equal to. I'm going to write it in brackets for now. We're going to have the upper bound n minus, now what's the lower bound? And again, I'm going to put that in brackets as well. Floor of n over 2 plus 1. Okay, and then it says plus 1 more. All right, the interesting thing here, we'll notice we get a minus, so the minus 1, or sorry, we get the minus on the 1, so we get a minus 1 and a plus 1, those cancel out. So we really just have here n minus the floor of n over 2. Now we can actually maybe use a little reasoning to think out what this is going to be equal to. If we didn't have the floor there, we would just have n minus a half, or half of an n. That would give us half an n. That makes sense. But when we subtract off the floor of the half of n, we actually get the ceiling of the half of n. And again, that maybe makes sense. Think of this for yourself. Say n is 5. The floor would be 2. The ceiling would be 3. 2 plus 3 is 5. That's how we get that there. So, so this whole sum that we were trying to work on here, that whole thing just happens to be the ceiling of n over 2. And we can approximate that. Now I put an equals there, but I do want to approximate on this step, so I'm going to do greater than equals as well to make sure we're going in the right direction. Now I'm going to do this ceiling of n over 2 first because it's easiest. The ceiling of n over 2 is greater than or equal to just n over 2 by itself. So when we're going in this direction, we can just drop the ceiling out altogether. We don't need to worry about it. The floor, on the other hand, is a little bit trickier. Let's just remind ourselves the floor of x, what is it greater than or equal to? Well, floors makes things smaller, so it's not greater than or equal to x by itself, but the smallest it can make it is 1 smaller. So we actually get the floor of x is greater than or equal to x minus 1, or in this case, we have the floor of n over 2 must be greater than or equal to n over 2 minus 1. The minus 1 cancels out with the plus 1. That's a little bit of magic there. We're still going to have our log, and we're going to have n over 2. All right, we're not exactly done here. We probably should do one more log identity. We're going to realize here that we're going to get n over 2 log of n. Now remember, log of a ratio like this, log of a fraction, is log of the top minus log of the bottom. So log of the top is the log n that we have here, minus n over 2, that's still out front, log of the bottom, log of 2. Maybe I'll continue right here. Just to simplify, we can probably see that this is going to be n log n all over 2 minus, and this log 2 is just 1, so we just get n over 2. This is our dominant term here, so we've shown big omega of n log n. Big omega of n log n, that actually matches what we had up here for our big O. So I guess all of that together is sufficient for theta of n log n. Okay, so there, let's just quickly go through again. We have sort of two techniques that we've introduced here. The first one I call binding the term, and we've used that twice, here where we overestimated log I with log n, and then again here where we underestimated log I with log of the floor of n over 2 plus 1. That's called binding the term. And then critically in the lower bound, we did this splitting the sum technique, and that's this step here, where we move from the sum from 1 to n, to the sum from the floor of n over 2 plus 1 to n. And we split that right along the middle. The plus 1 here looks a little bit ugly, but down the road it canceled out with a minus 1, so that was nice. We could have split it at other locations, but this one works just as good as any other one. So it works out pretty well too, because the n over 2 gave us log of 2, which was again another EC calculation. So a couple different techniques there. Now in my next video, I do want to practice these techniques a little bit more with a few more problems. Maybe I'll just introduce us to those problems here. Again, here I've got some of those techniques that we looked at here. The binding the sum above, binding the term below does not work. It's interesting, but not type bound. If we want a type bound, we'll do splitting the sum. That's what we did here. Overestimating or taking the total sum and underestimating it by half of the sum. And again, the technique that I introduced here, all of the tricks that we use are provided here. So I think we get right down to the same conclusion that we had here. And as I mentioned in the next video, I do want to practice this technique by looking at these sums here, and again practicing and getting familiar with both binding the term and splitting the sum. All right, thank you for watching, and we'll see you in the next video.